ID, The Future, a podcast about evolution and intelligent design.
So, Stuart, great to see you again. It was fun to see you a few weeks ago in England for the Insider's Briefing. Really enjoyed your presentation that you gave there.
Yeah, it was a great conference, I think.
Yeah, excellent. And we had a lot of great speakers, and certainly I know people appreciated your expertise and the experience you were able to bring on the engineering side, because we hear so many of these arguments about bad design and poor optimality of living systems that it's great to get a real engineer who knows what they're talking about. So you have published, if I'm remembering right, 2 recent papers, and you talked with our colleague Brian Miller pretty recently about one of the papers, which was about multifunctioning joints and lessons for robotics. Is that right?
Yeah, that's correct. Yeah.
Okay. Yeah, I listened to that. That was great. And I also appreciated the fact that you guys spent a little bit of time pushing back against some of the nonsense from the Darwinists like Nathan Lentz, who evidently don't have any knowledge about biomechanics or engineering. So it's great to see some pushback on that and showing that some of these claims are just ridiculous, frankly.
But yeah, I think engineering has a really important role to play in understanding biology. And often you find biologists don't understand, especially things like biomechanics. There's a lot of there's a lot of technical expertise needed to understand how joints work. So I think engineers have an important role to play.
Yeah, and I really appreciate the work you're doing because, in addition to the Darwin fanboys who are going to sort of glom onto anything that points toward evolution as they see it, there are a lot of people who are reading Nathan Lentz and others and being misled, which is really unfortunate. It's kind of sad to see. So I'm grateful for the work that you're doing to help set the record straight.
Yeah.
So let's talk about, before we do that, I think listeners already know you well. You've been introduced many times, but you're a professor of engineering at Bristol University, right?
Yeah, that's correct.
And I know you've got a list of published patents and papers longer than our arms, so we won't go through that list for everybody. But remind me what happened during the Olympics this past year. How did the UK team do on the Olympic cycles that you were working on?
Team GB again topped the medal table in terms of number of medals for cycling in the velodrome, which was very satisfying for me because I was again leading the design of the transmission system for the bicycles. For that, we had to go to some extreme levels of optimal design. So that was very satisfying. And there's definitely a link between the engineering I do and my interest in biomechanics, because in both scenarios, I'm very interested in what makes a system an optimal design.
Excellent. Yeah, we're disappointed that Team USA is coming in behind you guys all the time, but we'll have to get some better engineering on our side or something. By the way, I realized as you spoke there that I committed an American faux pas. I referred to UK, and you said it was Team Great Britain. So sorry for that. Right. We have trouble. We have trouble, as you know, keeping track in our minds of what's what. So thanks for that correction. Well, hey, today let's talk about your other paper, which is titled Universal Optimal Design in the Vertebrate Limb Pattern and Lessons for Bio-Inspired Design. That's a pretty long mouthful, but just briefly, what is this about? What is this vertebrate limb pattern that you're talking about?
Well, the vertebrate limb pattern is the arrangement of bones in limbs of vertebrates, i.e. mammals, amphibians, birds, reptiles. So, for example, in the case of the forelimb, the vertebrate pattern includes a shoulder, elbow, wrist. The upper arm has a humerus. The lower arm has 2 bones, the ulnar radius. Then there are wrist bones and digits. The hind limb is similar with 3 main joints like the hip, knee, ankle. Mm-hmm. Again, 2 bones in the lower leg. And so this pattern is very similar in land mammals, marine mammals, birds, frogs, and bats. It's a very famous pattern in vertebrates.
Right. And there's, of course, plenty of organisms that don't have this pattern, but this one's particularly interesting to us because it relates to us as humans. And so that's one thing that people get excited about. And talk to me a little bit about the evolutionary view of this. What was Darwin's view as he looked at the homology, if you want to call it that, and maybe we should probably even dive into what homology means. But as Darwin looked at the human limb and some of these other organisms, why did he think there was evidence for evolution there?
Well, I think this pattern of the vertebrate limb, which is similar amongst different organisms, hence the term homology, it's the similarity of the pattern. This was really, to Darwin, an iconic, what for him was an evidence for evolution, because he assumed that the vertebrate pattern was not universally optimal. For example, in particular for the whale flipper, he assumed that whales didn't really need an elbow, they didn't need a wrist or digits, they weren't really functional. And if Darwin was correct, and that's a big if Darwin was correct that the whale didn't need these features of the vertebrate limb, then you need the theory of evolutionary inheritance to explain their existence. So Darwin argued that the marine whales must have had a land-dwelling ancestor because they seem to have the features that land-dwelling animals have, this vertebrate limb. So to Darwin, this is really one of the things that inspired him for the theory of evolution. The vertebrate limb pattern was really important to Darwin.
Yeah, so just to unpack it for a second, the idea, let me restate it a little bit. You could correct me if I'm misstating this, but the idea is that because, according to Darwin, something like the whale's flipper is suboptimal, then there's no particular good reason why it's the way it is. It just, it's the way that it turned out. And so therefore, according to Darwin, we're going to dismiss the idea of design because surely a designer would have designed it more optimally than it is. And therefore, a more parsimonious explanation is that this is some type of kludge. This is some type of inheritance from the past. It is what it is. It's not a particularly great design, but hey, that's what it is.
Yeah, that's correct. I mean, he basically looked at the flipper and thought, well, to me, that doesn't look a good design. He said, this is not what I would expect for a flipper. But Darwin didn't justify that. He didn't understand concepts like hydrodynamic efficiency. He just saw a flipper as a stiff paddle that was just steering the whale. Why did it need these sophisticated designs inside the flipper? He assumed that the elbow joint, the wrist joint, the digits were not really functional. They're like vestigial organs that used to have a function that don't now. He just saw the flippers as stiff flippers.
Okay, so let's draw a line in the sand here real quick. So we need to recognize that Darwin's argument is an argument from ignorance. That's a point that we need to make clear.
Yeah, that's correct.
And is that argument, do we still see that today, Stuart? Are you still running across evolutionists that talk about that?
Yeah, I mean, it's a long time since Darwin wrote his book, over 100 years, but we're seeing the same arguments in textbooks today. You often read in a college textbook that the design of a whale flipper or bird wing is not what you would expect. If it had just evolved in isolation or was designed, it's not what you would expect. To see this elbow wrist, it's talked about as a strange design, just like Darwin did. But just like Darwin, there's no justification of that. There's no detailed explanation as to why it's not a good design. There's no explanation of what would be a better design. So things haven't changed since the time of Darwin.
Yeah. It's not what we would expect. And what would we expect? Well, I have never seen, I don't know about you, Stuart, I've looked at a lot of these kinds of arguments. To date, I have never seen an evolutionist support that kind of a claim with the detailed engineering analysis, whether you're talking about the mammalian eye, whether we're talking about the wrist joint, whether we're talking about the whale flipper. There's always sort of this ephemeral, gee, it looks odd to me, I'm not going to dig any deeper into it, it must not be designed, rather than really diving in and looking at how this system functions and seeing whether the design is good. So that's what I appreciate about what you're doing, and that brings us now to your paper. So what did you analyze as you were looking at vertebrate limbs and putting together this paper as you're getting ready to publish that?
Yeah, I analyzed 3 forelimbs, the human arm, a whale flipper, a bird wing, and I analysed 3 hind limbs, the human leg, cat leg, feline leg, and a frog leg. Actually, when I first submitted my paper, I just had 5 limbs, but the reviewers insisted that I add a 4-legged mammal for quadruped motion, so I added the cat limb. I think that was a good point from the reviewers. It made it a much better paper. I basically chose these case studies to get a range of functions like walking, flying, swimming, jumping. It was an enormous undertaking, so it would have been very difficult to do more than 6, but I tried to get a range of functions. And I chose the title very carefully because I wanted even the title to challenge Darwin's argument. Darwin had claimed universal optimal he claimed there wasn't universal optimal design. So I wanted my title to say universal optimal design of the vertebrate limb pattern to make it really clear I was challenging his homology argument.
Right. Okay, so let's jump in then. I'm looking at your chart here with your vertebrate limbs, and I don't know if we can bring this up on the screen later for our viewers, but you've got the human on the left, and then the next one is the whale flipper. So let's talk about that one first. Why do you think the whale flipper is a good design, and what are some of the patterns that you're seeing with that?
Yeah, it's quite an involved thing. Basically, the flipper is much more than a stiff paddle, as Darwin thought. The flipper is a variable stiffness and variable shape structure. The reason for this is that the flipper has an important requirement to have what's called high hydrodynamic efficiency. So basically what that means is that it must have high lift and low drag. It needs high lift to be able to apply large forces for steering during swimming, and it needs low drag to avoid wasting energy during swimming. So the flipper has a very optimal fusiform cross-section with a thick leading edge. But this is the really key point. For high lift and low drag, it's very important to fine-tune the stiffness of the flipper. The reason for this is that the forces on a whale flipper are always changing. Just to give you an extreme example, if a whale wants to decelerate hard, the forces on the flipper become huge. Imagine a blue whale weighing 200 tons and it suddenly wants to put the brakes on. The flippers experience an extremely high load, several tons. And so the flippers must be stiffened. Otherwise, they really deform and the drag coefficient goes right up. So when a blue whale is wanting to brake, it puts its flippers out, and at the same time, it really tenses the muscles in the flipper.
Right.
But actually, it's more sophisticated than that, because what the whale does, it fine-tunes the stiffness of the flipper by tensioning the muscles, and it fine-tunes it so the stiffness is just right for stopping the deformation, depending on what the loads are on the flipper. So it's a very clever design. I think the reason I think the reason people find it hard to appreciate this is that the muscles in the flipper are working in isometric contraction, not isotonic contraction. What that means is you don't actually see the flipper moving. And it's hard to appreciate that when a whale is swimming, unbeknown to us, the muscle contractions are constantly varying to fine-tune the stiffness. So there's something you don't physically see, but it's actually happening as the whale is actually swimming.
Yeah, I was just going to ask about something along those lines. So you mentioned the adjustments in the stiffness depending on the situation that it's in, and it could vary not just from day to day and hour to hour, but from minute to minute or second to second.
Exactly.
So there are presumably then sensors, I would imagine, within the limb that are sensing motion and force and adjusting the muscles, or sending signals to adjust the muscles based on what it's experiencing kind of in real time, right?
Yeah, that's a really good point. Recent research has shown that flippers contain many sensors, not just position sensors so that the whale knows it needs to contract a muscle in order to stop deformation. But flippers even have sensors that can detect vortices and complex hydrodynamic effects like that. So flippers are very sensor rich, and showing that they do have a sophisticated design.
Yeah. So tell me about this piece. I should have pulled up a photograph of a whale flipper before this conversation here, but do the whale flippers have a thicker leading edge and a more narrow back edge like an airplane wing for hydrodynamics, or how do they generate lift? Is it a similar type of design?
Yeah, it's very similar to an aerofoil. So the front is thicker, just like an aircraft aerofoil, and it has a similar angle of attack. So, it's a very similar process with the lift and the drag. In the case of a whale, you get more extreme movements actually because of the way hydrodynamics works. But basically, it's a similar principle of lift and a similar principle of drag.
Yeah, and I guess if you think about an airplane, you're typically wanting to go up all the time. The whale wouldn't necessarily want to do that all the time. He's wanting to go down as often as to go up, right? So it'd need to be a little more flexible than that.
Yeah, that's correct. And whales do some other interesting things. In the case of a humpback whale, they jump out of the water, and the flippers have to be very robust to survive that kind of crashing down on the surface of the water.
Okay. And one last thing on the whale flipper. So I'm looking at the digits in your drawing there in your published paper, and it looks like I'm seeing a lot more bones in, what is that, the second and third digits than in the human hand. Is that right?
Yeah, the human hand only has 3 joints, 3 bones, but whales can have far more than that, even over 10.
Okay.
But there's a very clever design feature because it means the whale can have a very smooth curvature. Sometimes the whale does want to change the shape of the flipper. Sometimes they may want to have a wing, the tip bent up to reduce the vortices at the end of the flipper. And so when it changes the shape of the flipper, it can produce a very smooth, changed shape. Smooth shapes mean lower drag coefficients. So in order to produce this smoothness, there are many bones in the digits, again, showing that the vertebrate limb pattern is good for the whale.
Right. Yeah, so you're talking about tipping up at the end, kind of like we see with the newer airplanes?
Yeah, very similar principle to that.
Right. Okay. Yeah, so optimal for that particular use. But the other thing I would point out here, and I know this wasn't necessarily the point you were making, but I just wanted to mention for everybody who's watching and listening today, if you're talking about a claim that the human hand, say, and the whale flipper have some shared ancestry or some shared homology, there are vast differences between the two. Sure, they've both got 5 digits, but the size, number one, is massively different. The shapes of a number of the bones are quite different. The number of bones that you have in the digits are different. So you have a significant number of changes that would be required from whatever starting point you're talking about to get to a human hand versus a whale flipper and versus, I guess we're going to talk about a bird's wing, for example. So each of these are, I would say, superficially homologous in the sense that, they both have fingers and some similar bones. And so it kind of sounds like, if you don't dig too deep and don't think too clearly about it, that maybe there was some, Darwinian evolutionary ancestry and they slowly morphed and turned one into the other. But when you really look at the details of what would be required to construct and maintain one of these systems, vastly different, even though they share some similarities in terms of overall form and function, which make them similar in some of the ways that they can bear loads and move and so forth that you've been looking at in your paper.
Yeah, I think that is correct. If you look at the details of my paper, there are some very different detailed requirements between, say, whales and humans for their forelimbs. So yes, there are some very big differences. But what I would add is that this also shows the great versatility of the concept of the vertebrate limb pattern that the same concept can be used for such different functions, whether it's leaping, running, swimming, flying. It does show the versatility of that concept.
Right. So you've got a design motif that is in play here with your large main bone. I guess I'm going top to bottom the way you showed it in your paper. Your large main bone, and then splitting into two bones that allow some rotation, then splitting into your wrist bones, which are many more, 7, 8, depending on the organism you're talking about, and then into the fingers.
Mm-hmm.
So you've got that design motif that you can identify down through each of these systems. But the devil is in the details in terms of how it's implemented and whether it works for that particular environment, for that particular organism.
Yeah, that's absolutely correct. It's also worth adding that in human technology, engineers often use a design concept that kind of mirrors the vertebrate limb pattern. If you look at the design of a digger, it has an elbow, a shoulder, a wrist. The same for spacecraft solar panels, the same for robots. And that adds weight to the thesis that the vertebrate limb pattern is a universally optimal design.
Yeah, you've got a design motif that'll work with a lot of different systems. Good.
Yeah.
So unlike Darwin, who thought, well, because there's some superficial similarity here, or there's the same design motif here, let's call it, therefore it must not be optimal for each one. And therefore there must have been some kind of evolutionary process. You're saying, no. If you look at yes, they're the same motif, but there's good reasons for that. And if you look at the details, you find that each one is optimal for its particular situation.
Yeah, that's exactly correct.
Okay, good. Let's talk about the bird wing for a minute.
Well, really, it's really quite a similar story to the whale flipper, because a bird wing needs to, again, have a variable stiffness and a variable shape design, just like the whale flipper. The forces on a bird are constantly changing. There are gusts of wind. It slows down, it speeds up. But it doesn't want the wing to deform, especially if it's, for example, gliding. So to stop the wing deforming, it needs the joints, the wrist joint, the elbow joint, the finger joint, and it needs all the muscles to contract in order to vary the stiffness. So just like the whale, if you watch a bird, say, gliding, you might think, oh, those wings are static. But actually, that's not correct. The muscles are actually working hard to fine-tune the stiffness in order to stop the wings from moving. Interestingly, most birds have more than 25 muscles in each wing, and they're fully functioning muscles. And that gives you this hint that there is this sophisticated design for fine-tuning stiffness.
How does that compare with humans, if you happen to know off the top of your head? How many muscles do we have in the similar?
Actually, in our forelimb, it would be, 25 muscles for our arm, but then another 36 in our hand. So humans have more if you're looking at the whole of the forelimb.
Right.
But I think most people are quite surprised when you tell them there are over 25 muscles in the wing of a bird. People often assume, that's separate for the flight muscles. A lot of people think, well, it's got flight muscles, but then that, a bird doesn't need muscles within the wing to fine tune the stiffness and the shape. But yes, birds do have all of those muscles for that fine tuning.
Okay. And they have to be tuning those again, like we talked with the whale. You've got moment to moment changes, whether you're going up, whether you're going down, whether you're being chased.
Yeah, that's right. But one thing I would say about the birds is they also do change the shape of their wings. They will lift up the wingtips for efficiency. And that's where they're using the muscles in their wrist joint and their finger joint as well to move. They're able to move just the wingtip feathers or all of the primary feathers. They can move them in extension or move them in pronation. Birds can move their feathers in a surprisingly precise way.
Yeah, excellent. Well, as long as I've got a bird expert on here, do you happen to know what the velocity is of a laden swallow?
No.
African or European, right? All right. Here we go. Let's see. So I'm looking at your chart again. So we talked about a little bit about the human hand. Or the human arm. We talked a little bit about the whales and the birds. What about the back, limbs, like the human leg and the feline hind limb and the frog hind limb?
Yep. Well, the triple hinge layout is ideal for running.
Mm-hmm.
But one thing I would say about the double limb in the lower leg, these kind of features help the fine tuning of mechanical advantage. Again, this points to the versatility of the vertebrate limb pattern. For the human leg, the frog leg, the cat hind limb, it's possible to have the mechanical advantage, so you can get high force and power from the leg muscles. It turns out that it's so optimal that robot engineers are actually trying to copy some of these features into four-legged robots and two-legged robots.
So is there something about, I don't know if you've studied this or looked into this, but if you look at something like a cat jumping or a frog jumping, is there something about the bones themselves, or is this primary the ability? Here's what I'm talking about. Let me back up. The ability that they have to jump such incredible distances, does that relate significantly to the bone structure, or is that primarily building up tension within the muscles?
Yeah, it's quite complicated. If we take the example of the frog leg, there are some quite astonishing fine details in the design of frog legs. They do have particularly lightweight and very stiff bones,
Okay.
more stiff and lightweight than other kind of animals, to help their jumping. In the case of frog legs, they have a universal joint in their knee. They have more freedom of movement in their knee to enable them to direct the force more directly from their center of gravity into the ground. So there's no bending in the knee, and they have other particular features. They have an extra joint in their foot, so they can keep their feet on the ground longer to get more kind of exit velocity. So the frog is an example where the vertebrate limb pattern is kind of has a very special expression in order to optimize jumping.
Right. Okay. Very interesting. And then if you look, so for example, at the human leg, you mentioned the two bones in the lower limb, which
Yeah.
give us what? The ability to rotate?
It gives stability to the ankle, and not, because you need your two bones. It's a bit like a car suspension system. It's very much connected with the ankle. Not only stabilizes the ankle, but also enables fine tuning of the mechanical advantage of the muscles of the foot, particularly the ones that rotate the ankle.
Right. Okay. And you mentioned some differences in the frog bones being a little more lightweight. Now, bird bones are also incredibly lightweight, correct?
Yeah, that's correct. Not just hollow, but some birds even will have a truss kind of structure inside their bones. Again, showing that even though you have this vertebrate limb pattern, there are actually, when you look very closely, some really quite striking differences between the limbs of one animal and another.
Right. Which again seem to be optimized for their particular use, right?
Yeah, exactly.
Yeah, you're talking about flight, you're talking about battling gravity much more so than a terrestrial animal or an aquatic animal. And so you
Yes.
need all the
Yeah.
lightness you can get, and probably a little less important to have incredibly strong compression capabilities. Whereas if
Yeah, that's right.
if you're running and jumping,
Yeah.
a horse or something like that, you're going to have really important compression.
Yeah, that's correct.
Yeah. Okay. Good. So talk to us. I know you do a lot in robotics. As you look through all of these different limb patterns and kind of analyze what we see in nature, how is this relevant for the robotics work that you and others are doing?
Yeah, it's really very relevant for robotics because in terms of mechanical performance or things like locomotion, robots are way behind the performance of animals. You just look at a humanoid robot trying to run. Normally it can run very slowly, only in a straight line. So engineers are really keen to understand, why is it that animals, cats, can run so fast? Why are they so agile? And more engineers are looking to copy the design features. By copying cat legs, we can make better robots. We can make better hydrofoils by fine-tuning stiffness in the way a whale does it. We can make better drones by copying features of bird wings. The fact that we can make better robots by copying the vertebrate limb pattern, I think that adds weight to the fact that it is this universal optimal design. In fact, what I would say is that if engineers followed the advice of Darwin, then they would not be copying the vertebrate limb pattern. And that would be an example where evolution is holding back science.
Yeah, absolutely. Yeah, this is a clear case where the theory of evolution runs smack into the wall of reality and doesn't hold up at all here. So good. Well, I'm just looking through your paper here. You've got, and we'll try to, is this open access? Can people get a copy of this?
Yes, it is. When you publish with the Institute of Physics, it's normally not open access, but my particular paper was granted what's called golden open access because they labeled it as a review paper, which is then considered a state-of-the-art important paper. So that was a very pleasing thing, but it also meant that it's open access. So anyone, the public, any researcher, free of charge can see the paper.
Excellent. Yeah, I first of all, congratulations. That's fantastic to get that status. And we will definitely provide a link so people can look at the paper. I have to tell you, there are just dozens of diagrams and images in here that people can look through to better understand what it is that you're talking about with these different joints and the different limbs and how they function. So this is absolutely fantastic.
I was just going to say it's been 3 months since this has been published. Mm-hmm. It's been quite encouraging. There have been 2,000 downloads, which is quite unusual to have 2,000 after 3 months. It's actually already been cited 3 times by other secular papers, and it would normally take about 2 years to get to 3 citations. So it's already definitely generating quite a bit of interest in the community.
Wow, congratulations. Well, yeah, that's fantastic to hear. And it also just, I think, points to the fact that people are eager to understand what's actually going on. The lazy sort of stuff just kind of falls in place and works evolutionary story doesn't provide any answers that are useful. And when you actually take an engineering approach, dig into the details, understand how these systems are working, understand how the various parts fit together to perform specific functions, that's really valuable for people. And I think that that's a real testament that people are already citing your paper. So congratulations on that.
Yeah, thank you.
So as we kind of go back to where we started the conversation, Darwin looks at these different organisms, notices some basic similarity in the motif, we'll call it, of how these are put together, assumes that they must not be optimal and therefore they weren't designed in evolution. It's evidence for evolution. As you've gone through this in detail, and I know you've spent years looking at this, what's your assessment of whether we're looking at limbs that are really optimally designed or poorly designed?
Yeah, I've been studying these limbs for over 30 years. And yeah, there's no question they are really, really optimally designed. And in my paper, I make a recommendation to robotics engineers that in every case, but all the land animals, the marine animals, birds, I said in every case, engineers should be looking to copy these systems, not holding back. Mm-hmm. I've really been astonished at the level of optimality. What's interesting is when I've looked, because I have 120 references to my paper, in every case, I've read papers where the researchers have said things like, the design of frog legs is astonishingly complex. And they were clearly not expecting this sophistication of design. So I found that one of the most fascinating things. It kept cropping up. We were not expecting such an astonishingly complex design.
Yeah, that's beautiful. And it really gives the lie to the argument that we still hear today, unfortunately, that, life is poorly designed. Things are just a kludge that are thrown together by chance and accident. And so I'm just so grateful that you're doing all this tremendous work, and we'll try to do our best to make sure that people are aware of this and appreciate it for all the fantastic research that you've done here, Stuart.
Yeah, thanks for your help too, Eric.
Thank you for listening to this episode of ID the Future. To learn more about the remarkable engineering in life, Join us again at idthefuture.com or at our YouTube channel, Discovery Science. And help us spread this important message by sharing a link with a friend. For ID the Future, I'm Eric Anderson. Thanks for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.